What's up, calculus students? Today we are going to be doing the shadow or the street lamp problem, which is a related rates problem from our unit 4. And here's the setup. We'll see, we may have different ones. It could be the shadow problem. There's also the related volumes. We did a project on that, if you remember. But this is the shadow version of those problems. So, a 6-foot tall man walks at 5 feet per second away from a 20-foot tall street lamp. A, when the man is 7 feet away from the lamp, at what rate is his shadow growing? And then B, when the man is 10 feet away from the lamp, at what rate is the tip of his shadow moving? To do this with all related rates problems, the first thing you're going to do is draw a diagram. So I'll draw a little lamp post here. I don't know why I'm trying so hard, but see, it's a lamp post. This is 20 feet tall. And then we have a 6-foot tall man. He's got short arms and they're a little off center. Whoops. Okay. 6-foot tall man, and he's walking away at 5 feet per second. So when we're doing one of these problems, let's look at A. We're trying to find the rate at which his shadow is growing. But we don't actually right now know what his shadow is. So we're going to draw a triangle to give us kind of a diagram of what his shadow looks like. So we know that's how the light is going to cast, and that this length is going to be his shadow. See, it's a dude. Look at that, short arms. So that's his shadow, and we're gonna call that S. And then we've got a distance, which apparently comes into play. We'll see if that actually matters. We've got the distance between him and the street lamp, and we'll call that X. So what we're trying to do is find the rate his shadow is growing. So first let's think about what we know. We know that he's walking at 5 feet per second, which tells us that X, or the derivative of X prime, with respect to time, is 5 feet per second. In other words, this is growing by 5 feet per second, which gives us its rate of change. So we know the rate of change of X. We don't know the rate of change of S yet. However, we know that these are two congruent triangles, actually. If you look within the big triangle made by the street lamp, there's also the smaller triangle made by the man, and all the angles are exactly the same. You have 90, and of course this is the same angle, so this one has to be the same. So when that happens, we can have a proportional ratio, or basically what that means is 6, the height of the man, is to S, as 20, or the height of the street lamp, is to X plus S. This entire distance, we'll call it L when I'm just referring to it. So whenever we have a ratio, a proportional ratio like this, these fractions, we can just cross multiply. So we get 20S equals 6x plus 6s. We can do a little bit of math. I've done it like a million times trying to do this, so I'm just going to skip through. S equals x over 2. So now we have an equation, and it doesn't seem like we're going to need the whole 7 feet away from the lamp. Let's just take the derivative of both sides, because that's what we're trying to find, right? We're trying to find the rate of change of S, and we know the rate of change of X. So with respect to time, so remember, the X won't just disappear and become 1. We're going to take it with respect to time. So you'll get on one side S prime times 1, technically. I'm not going to go into the details of that. And then the same thing up here, X prime times 1 times 1/2. You can take out the constant. Remember, when you're taking the derivative, I just left it in there. And so we have S prime equals X prime over 2. So we already know X prime over 2. So we can just plug that in, and we get 5/2 feet per second. Or in other words, his shadow is growing. I can't talk fractions. His shadow is growing at 2.5 feet per second, or half as fast as he is walking away, or the distance between him and the street light is growing. And that's problem A. We've got our answer. The rate at which his shadow is growing is 2.5. It doesn't look like actually the distance he is away from the street lamp will actually matter. But you may have an equation where where time or another related rates problem, especially with cones and stuff like that, where the amount of time has passed significantly alters the rate at which something is changing. So yeah, let's do B now. All right, part B. Part B is actually a lot simpler than part A because, well, first of all, let's just look at what we have. We're trying to find the rate at which is the tip of his shadow is moving. So that's not just how fast his shadow is growing, but how fast X is growing as well. So it's this entire length, and as I've noted, I'm going to call it L. And we could reset up this equation, plugging in L for X plus S, because remember L equals X plus S. But we should, first of all, we can just try, as with any related rates problem, you want to write down all the formulas you have. We know L equals X plus S. And with a function like this, we can just take the derivative of both sides with respect to time. So L prime, or dL dt, is equal to X prime plus S prime. And we know both of those, which is what makes this problem so much simpler, is we know that S prime is 5/2 because we just found it, and we know it's constant. There's no variable in containing how far away it is, how far away the man is from the lamppost. So we know that we can just say S prime is 5/2 for any point where the man is. And so we can just plug those in. We know he's walking at a constant rate. X is constantly changing at 5 feet per second. So the tip of his shadow, or the full length of this, diagram, is equal to, or I guess the rate at which it's changing is 5 plus 5/2, which equals 7.5. So in English, the tip of his shadow is moving at a rate of 7.5 feet per second. And that's it. I hope this isn't too easy to get credit.